what I'm going to do in the next hour is provide the taxonomies that I'm going to use through my talk, speak a little bit about main programming models that are used, and if there is one thing to remember from my talk, it's never this is better than this. It's always trade-offs. A is better in this aspect and worse in that aspect. No magic bullets. Taxonomy, the terminology I'm going to use in my talk. When I speak of programming model, I speak of a set of operations and a set of constructs that we're using to express parallelism. So for example, from my perspective, Java and C++ embody or implement the same programming model. Very different languages, but the programming model is essentially the same. And the programming model can be implemented by a library. Message passing can be implemented by MPI, for example, can be implemented by a language. One implementation, one programming system, like MPI, can oftentimes support more than one programming model. And we shouldn't confuse the two. You can use MPI to write message passing code where one process sends, the other receives. You can use MPI to write one-sided code where you use put-gets to get into remote memory location. You could use MPI for very synchronous code. You can use MPI for very asynchronous code. So MPI does support multiple programming models. It is one system. Now, the point that I want to emphasize, and I will return again and again in my talk, we always think of programming models as in terms of their semantics. What is the outcome of the computation as defined by the semantics of the language or the model? If you are in this room, you care about performance. And you care to understand what will be the performance of your code, more or less, when you write it. It's not blind trial and error, trying one thing and another, and see eventually what performance you get, what's the best way of getting the performance you want. So informally, programming models, programming systems also have some performance model associated with them. You know that if you write a sequential code, then the time to execute the code will be more or less proportional to the number of instructions you execute. The number of instructions in the loop is the number of iteration times the number of instructions per iteration, and so on and so forth. So there is an intuitive programming performance model. The problem is that we never bother to define it very, in a very formal manner, and it's hard because implementations sometimes are not that faithful. But it is very important, and it is very important to keep in mind what is the implicit performance model of the programming models that you are using. Final introductory slide. When you think of a programming of a parallel system, of course you have at the bottom the hardware, but none of us are programming, or almost none of us are programming directly to the hardware. Usually you are insulated by an operating system and runtime. These raise the level of abstraction than you are getting from the system, give you higher level programming models. And a lot of debate when we speak of programming models is what should be in these layers that translate essentially the hardware as it is given to you to the programming model that you write your code against. And some of this runtime can virtualize resources, can hide details of the hardware, and give you a different programming model than the one that is more natively supported by the hardware. You heard this morning about architectures, so I'm not going to speak at length about architecture, but just to have one reference point. That's the way I think of a node. A node is a bunch of physical threads that execute sequential streams of instructions. These physical threads can have, and today almost always have, some SIMD unit or vector unit, which gives you some level of parallelism of SIMD parallelism, where you execute simultaneously the same operation on entries of a vector. Then you have a fairly deep memory subsystem, and after the talk of Pete, you know that it's even more complex than what I've shown here. But basically, you typically have tree hierarchy where it's close to the physical thread, you have caches that are more private, and the further you go down, the bigger, the slower is the memory hierarchy, the larger it is, and the more shared it is by more of these physical threads. So that's a very high-level view of the architecture. And if we are in shared memory, we communicate across threads by doing loads and stores. We also communicate to memory, or memory to cache, or cache to cache, using load and stores. Increasingly, we can take advantage of prefetches. Hardware provides us prefetches. It tries to guess when it sees a stream of loads what will be the next load, and therefore brings this value into the cache. Most modern, all modern microprocessors probably have software prefetch, so you can actually bring stuff into your cache ahead of time to make sure you won't have a cache miss when you actually need the value. And you synchronize using a variety of read, write, modify operations. Again, nothing that you don't know. Mutual exclusion operations of one kind or another, logs, atomic updates. One thing that I would like to point, most of the synchronization operations that are provided on shared memory architecture are some form or another of mutual exclusion, symmetric synchronization. Either I go or you go. We don't go at the same time, but we don't know which of us two will go first. There are a few synchronization operations that are asymmetric, that are ordering, where I know that I go first and you go first, and then you go after me. You can use something like a monitor wait, which on an Intel chip is actually supported in hardware, to impose an order. You know, I monitor a particular location and wait until it's updated, and I will execute only after you update this location. But typically, it's hard on current shared memory systems to impose a particular order of execution, which is a pity, because in high-performance computing, you have much more use for synchronizations where you order who comes before who, rather than synchronizations that are just mutual exclusion. You heard a little bit about the evolution of these architectures. Clearly, the number of physical threads continues to increase. Clearly, the depth of the memory hierarchy is increasing. It's not obvious that we shall have caches. We may have scratch pads instead of caches, or some variant or another of local storage that is not coherent in one shape or another. We heard this morning two views, coherence forever, or coherence is way too expensive. So pick your own, hard to know, of course. And clearly, shared memory becomes more and more NUMA. The view that memory access time is uniform is increasingly false when you have more and more chips, more and more memory channels or memory attached to your multi-core processor. And the other thing that is happening, and again, a huge debate of where we shall be in the future, we increasingly have systems where not all physical threads are identical, heterogeneous systems. We may have threads which are more GPU-like, physical threads that are more GPU-like, physical threads that are more CPU-like. And again, pick your position on this debate. Some believe that future architecture will be uniform, but that threads will have fancier SIMD instructions. Some believe heterogeneity is essential to save energy, because you can execute on the most appropriate thread codes which have different properties. And even if you have different threads, you still have the choice. So are there threads which have different instruction set architectures that make life really miserable? or are there threads which have the same ISA but may have different features in terms of their execution speed or what codes they can execute faster. And then we have the next level of connectivity connecting multiple nodes. And you heard a little bit about from Pavan about such hardware. The only issues that I want to mention, when you look at modern networks, they support fairly directly point-to-point communication. I send data on a channel, you receive it at the other end of the channel. They support increasingly one-sided communication or remote direct memory access. You can do a get operation where you read from remote memory. You can do a put operation where you write into remote memory, or you can do an atomic update to remote memory, things like a remote accumulate, for example, to accumulate, to add values into a remote memory. And these kind of operations are supported by the networks we're using, the interconnection networks we're using in high-performance computing. We also have support typically for one form or another of collective operations, like barriers or a reduce operation, where we globally sum values from all nodes or from a set of nodes or a broadcast. Unfortunately, for the reasons that were mentioned before by David, this becomes less and less efficient if processors don't work at the same speed. And the final point about networks, we like to think of networks as flat. Each node is as distant from any other node, or the distance between any two nodes is the same. This approximation becomes harder and harder to support when you go to larger networks. So a topic of research that was very popular when supercomputing or when parallel computing started, how you map an algorithm to a particular topology, unfortunately, or fortunately, depending on what you like to do, is becoming back in fashion. Performance model, programming models. Let's now discuss programming models. The simple-most programming model you can think is a programming model that reflects pretty directly the architecture that I've outlined. So you will have a fixed number of physical threads. You can have one thread per core, or if they are multi-threaded, you may think of 2 threads per core or 4 threads per core. The threads are physical, they don't move, they are pinned to core, so fixed number with each one backed up by a fixed physical resource. You have a fixed amount of memory on your node. This memory is shared within the node. Then a fixed number of nodes, and the nodes communicate by the primitives that I discussed in my previous slide. What is the performance model that you are using? At the first level of abstraction, you assume that all your physical threads are computing at the same speed. You assume that memory is flat, or you can ignore to first approximation time to access memory. You assume that when you go out of the node, you communicate with another node. The communication time, again, if you assume that the topology is flat, which I said becomes harder, then communication time is going to be essentially proportional to the amount of data you try to send from one node to another. Typically, we use a simple formula of this kind, some fixed overhead per message plus some time that's proportional to the amount of communication. So that's a simple-minded model. You can slightly refine it, but that's typically at the level at which we start designing parallel algorithms. And by the way, that's a programming model that you can program into if you are using MPI to communicate across nodes, and you are using piece threads inside nodes, and you make sure that you have that threads don't migrate, that each thread is attached to a particular core. That's the way you program. And you will learn in the future about OpenMP, and OpenMP is a shared memory programming language. It allows to do many things, smart or silly, but you can program an OpenMP program in this style where you have a fixed number of threads, each one attached to a particular core. What's the pro and con when you program at this level? you are very hardware specific. You can carefully optimize your algorithm to the hardware. It's very low end, very easy to get your program wrong, very hardware specific, which means that when you move to another machine, you have to change your code. It's parameterized by the number of threads, by the number of nodes, so it's very hardware specific. I have not spoken about heterogeneous cores, so I don't know yet how to take care of GPUs or other strange animals. And as we already heard, the simple models that equal compute work means equal computation time is breaking down for a variety of reasons. Power management, handling of errors in particular. So people think that low-level programming is bad, so they try to develop high-level programming models. High-level programming model, in my mind, you do two things. You virtualize some of the resources, so you don't program to a fixed number of threads, but to a varying number of threads, or you don't assume that you know exactly how much memory you have because you have virtual memory. So you virtualize resources, and you let the runtime map your virtual resources onto the physical resources that you have. And the other things that we often do when we move higher in the level of abstraction, that we try to restrict the type of or the programming patterns that we're going to use so that we get programs that are easier to understand, easier to get correct, easier to handle by the runtime, and so on and so forth. And I'm going to give you a few examples to explain what I mean when I say these two things. Now, we go to a higher level programming model, we still want to have a performance model. We want to be able to analyze how long it takes to execute this code. So it has to be that we have a way of defining the performance of high-level code, and that the runtime, when it maps it to the lower level, to the actual hardware, actually satisfies the assumptions that we made about what should be the running time of the high-level code. And let me, rather than continuing with this slide, really the only point here that I want to emphasize, what we find typically when we go to a higher level of abstraction, that it's always possible to write codes that are breaking the abstraction, where the programming model, the performance model that we assumed when we started is really not the right one. We are in a corner case. To pick the example of virtual memory, it's very easy to write code which is going to thrash because it keeps moving across pages. Most of the time it doesn't happen. It's also something that any reasonable programmer knows, that you have to be careful about, what is your working set, and try to make sure that your working set fits in memory and it doesn't change too rapidly. So that's an example of a programming style which we use informally, which makes sure that the abstraction of virtual memory actually works and we don't have to think about paging overheads. And when you go into parallel programming and high-performance computing, you will find that again and again, that you have to understand what are the boundaries where the abstraction when you program at a higher level is valid. And I'm going to go through one or two examples of this kind. Let me start with a very classical example. It's actually, I think it's one page, so you can read it. Go to statement considered harmful. Note the Dijskra sent to CACM, I don't remember how many decades ago. And his point was that it's very hard to understand programs that are using jumps or go-tos in an arbitrary manner. The execution is a spaghetti. It's very hard to understand where you are in the execution. On the other hand, if you use only well-nested loops and procedure calls, actually the connection, the relation between the static program and the dynamic execution is quite easy to understand. You need to understand what's your current instruction that you execute, the instruction counter if you wish. You need to know what is a call stack of procedures, the nesting of procedure calls. And if there are multiple loops, you need to know what is the index of each loop that you are in the middle of executing. These three things, the instructions that you currently execute, the stack of calls, and the indices of the loops tell you precisely what is your state in the execution of your program. So the mapping from the static program to the dynamic execution is easy to understand, therefore it's easier to avoid errors, it's easier to get correct programs. Furthermore, and that was also important, this restriction really doesn't cost you because there was already the knowledge at the time that you can transform programs that use gotos into programs that don't use gotos without losing performance or without losing performance most of the time. So that's an example of what I call going higher level by restriction. You know, when you don't use gotos, you use less of the language that you could before when you had gotos, but it turns out that this restriction doesn't really cost you, and it gains you a lot in terms of clarity of programming, ease of programming, and so on. Now let's go to shared memory programming, and let me show a few examples of those. Ones that you know very well. In a sense, when you program, you don't see the caches, isn't it? You program to a flat memory, you do a load store, and you don't know if it goes to cache or if it goes to memory. In fact, what you have done, you have virtualized memory. It's another form. Paging is one form of virtualizing memory that you don't know if it's on disk or on your memory. Caching is another form. You really don't see whether the data is in a cache or is in the main memory. And the performance model that you intuitively think about when you write a program is that the caches, the speed at which you access data is the speed of the cache. The size of your memory is the size of the DRAM. That's the illusion that caching is supposed to provide. And that's the intuition we have when we write programs. Now, we know that we can break this illusion. It's quite easy to write nasty codes where this illusion will not hold. We also know that many times it does hold. And in fact, we know how to write programs so that this illusion will actually be correct. Basically, we have to write programs so that they have a high cache hit rate. And getting a high cache hit rate is essential for performance today, because without that, you lose an order of magnitude in performance or more. Caches are more than an order of magnitude faster than main memory. And it's important also for reducing power consumption, even more important in the future, as we heard from Kogi, because most of the power is going into moving data, so you don't want to bring data all the time from memory, you want it to be in cache. The rules of the game to get good cache locality are well known. You need locality, which means temporal locality. If you bring something in the cache, you want to reuse it again and again. Spatial locality, if you bring a cache line, you want to bring it not just for reading one word. And the other point, which is sometimes forgotten, thread locality. If one thread accesses a particular datum, you don't want another thread to access the same datum nearly the same time. Otherwise, you ping pong. In fact, cache thread locality, you have to think of false sharing, so you have to make sure that if a thread accesses a cache line, another thread doesn't access that same cache line nearly at the same time. And the performance model, this performance model, speed is L1 speed, volume is DRAM volume, L4 volume, works well for codes that satisfy, that have good locality. So in a sense, we build a higher level model with virtual memory or with caching, and we have rules where the performance model, which is implicit in this high level model, is correct. And the rules are, please make sure that you have good locality. Let me give you another example, again from shared memory. I started by a model where I have a fixed number of threads. It's very convenient to program in terms of a variable number of threads. And I give you the simplest example you can think of. You want to do a reduction. Well, you start by you want to sum up 8 numbers. You start by computing 4 sums. You continue by computing 2 sums of sums. And eventually, the final sum, that's a parallel algorithm. Of course, you can write it. Well, first, if you sum 8 numbers, you will do it sequentially. Don't try to do it in parallel. Let's pick that only as a generic example, not as a real code that you should write. But it's more convenient to think of these 3 than to think of how I'm going to do it sequentially or how I'm going to do it in parallel. You would want to think about these 3 of tasks with these dependencies and have a runtime that somehow maps these tasks to your physical threads. Can we do that? So we have a task graph. In this example, by the way, the task graph is static. You know exactly what you compute. In general, the task graph may be dynamic. You don't know ahead of time what tasks are going to be executed and what are the dependencies, but the graph can grow as the computation goes on. So let's think about, and again, parallel computing 101. Let me remind you of basic definitions. You have a computation, we speak of the work, the total amount of operations we have to do. We speak of depth or span, which is a critical path length in this graph. How long, what is the shortest path in this graph? Clearly, the best we can hope to compute in parallel when we have P physical threads is work divided by P. P threads cannot cannot reduce the amount of time by more than P from the sequential time, which is the work. And also, clearly, we cannot find the critical path lengths in our computation. You may think of that as a form of Amdahl law, which it is really a generalization of Amdahl law. So we know that we cannot do better than the maximum of these 2 values, and we would like to have a performance, and our performance model, which is convenient to use for general task graphs, is to assume that indeed will be the time of the computation. Can we do that? Well, clearly we cannot do it in general. We need some restrictions. One restriction, which is obvious, if I allocate a task to a physical thread, it will cost me something. There is some operation to be done, scheduling a task on a core. It takes time, and I need my task to be at least large enough, or as large as the time it takes me to allocate, or larger. The amount of computations that I will do in this task has to be larger than the time it takes to schedule this task. So that's one obvious constraint. And remember what some people tend to forget, that the overhead of scheduling a task on a core is not only the actual time it takes to the runtime or the operating system to schedule the task, but also the time it takes to fill the cache of the core in the case the task was not running before on that core. So, you look at typical shared memory systems today, and you need a task to have thousands of instructions in order for it to be worthwhile to be scheduled on a core. So that's one obvious restriction. Another restriction, which is less obvious, if you have a static graph, if you know ahead of time everything you're going to compute and what are the dependencies between the pieces of computation, then you can compute the schedule, an optimal schedule, map it nicely onto your threads, physical threads, and execute. But if you have a dynamic graph, and in a sense the graph is getting built on the fly, then it may not be that easy to schedule it optimally. And people have worked on this problem over years, and the type of results that are known, that if you have a well-behaved or well-structured program, then you can actually do this mapping on the fly. What do I mean by well-mapping program? I assume that a task can spawn subtasks, a task can have children, and I assume that a task may have to wait for another task to complete, but the task can only wait for its children. It cannot wait or depend on what another task somewhere else is doing. So if you are using a parallel program model where a task can spawn children and then has to wait for the children to complete, or a task spawn a child and later on join back with this child, or a parallel programming model where you have parallel loops. So you start with a sequential thread of execution and you can branch into a parallel loop. Then you get this kind of nicely structured task graph, basically a series parallel graph or an and/or graph. A node can be followed up by another node, or a node can split into two children or more children, and then they merge back. And of course, this can be nested. Here I split into two, split further into two, merge back, merge back. And it is well known that for this kind of, for computation models that have this property, that they lead, by the way, what I've shown here is the execution graph. The task split it into two subtasks, merging back, and so on. For programs that lead to this kind of well-nested execution graphs, we can map the tasks onto physical threads so that the total compute time will be maximum of work divided by number of threads plus depth, critical path length. And by the way, you can program in this style again if you are using P threads or you're using OpenMP, but you have to restrict yourself. OpenMP or P threads allow you to write programs that don't satisfy this constraint. So that's an example again of a constraint that you can either impose by having a programming language that only allows this kind of constraints, this kind of code, or you can impose by telling the user, please don't use locks and please don't use other type of synchronization between tasks. Make sure that you only synchronize a task with its children. If you do that, then you know how to schedule dynamically the tasks. And typically the way you do it is using work stealing. And work stealing, again, is very simple to explain. Work stealing, the idea is that each core or each physical thread maintain a queue of tasks to be executed. When a thread branches, it puts the other tasks that it has generated into the queue and starts executing one of the branches. When a thread finishes executing a task, it picks another task from its queue. If its queue is empty, then it goes and steals a task from another queue. So I think I have an animation, must have an animation. So the first task here has started a new task, put it in the queue. A new task is created, goes into the queue. The first task is finished, so it picks from its queue another task to execute. A second task was created here. It's now scheduled, so it goes here. The first, well, my animation is far from perfect. The first thread has finished and picks the task from the other thread. And you know, there are a lot of theoretical results that are known about work stealing. It's theoretically optimal. It actually works well in practice on shared memory. It handles well variance in thread speed. You don't need all threads to run at the same speed to do work stealing. It has one problem, of course. For this kind of approach to works well, you want more tasks than physical threads. So you go into what we call over-decomposition. You partition your problem into more pieces than you have actually physical threads, which allows you then to do load balancing or move stuff from one thread to another, but means that you work with a problem that, or you partition your problem to a higher level than the number of physical threads that you have. And typically, the more we partition our problem, the less efficient is a parallel algorithm for a variety of reasons, so there is a trade-off here. We partition more, we get better load balancing, but the algorithm overall may start being less efficient. So that's shared memory, and shared memory is nice, and we like it. Can it work beyond one node? And people have tried forever, and there were years when it was popular to work on something that people call distributed virtual shared memory. Every student, every second student had a prototype of distributed virtual shared memory. And the idea was, okay, we understand how shared memory works. We have cache lines, we have coherence, and we bring cache lines when we have a load that requires this cache line. Let's do that across multiple nodes. So we don't have hardware coherence, we have to do it in software. You can do it with pages. So page now becomes a cache line. If you, a cache miss now become a page miss. And you have the pager being executing the coherence protocol. Works wonderful, semantically correct. You get coherent shared memory. Performance always has been abysmal, because when you have cache lines which are 4K, you have false sharing left and right. It takes much too long to service a coherence miss. So very good example, you get perfect semantics, the performance model is totally screwed up. So this doesn't work. As we heard from multiple times already, okay, we need to give up caching, we need to give up coherence, we give up dynamic task scheduling, but perhaps we preserve the global address space, so we shall have still an illusion, if you wish, of a global memory. We can access each part, each word, wherever it is on our big exascale machine. And there are several languages which support this model, PGAS model, languages like UPC or Core Fortran, or libraries like global arrays. What is a model? The model is basically that you are going to split the memory of each node into one part that contains private variable and one part that is used for global variables. Global variables can be anywhere. So basically it means that you have two types of references. You have references that point out to private memory. You can have, for some of these languages, a local pointer that points to the local part of the shared memory. And of course, you have global pointers that can point to your global part of the shared memory, or global pointer to point to a shared memory somewhere else. What's a local pointer? A local pointer is an address. What's a global pointer? It's an address and a node index. Nothing magic here. There is every parallel machine has a global address space. The address is node ID local address. The question is how efficient it is to use these pointers. So what is a performance model? How efficient? It really comes back to the question, what is your performance model in the PGAS language? And it turns out, in fact, it's quite obvious, that the performance model is not one of a shared memory machine, because when you do a remote access, it is much more expensive, orders of magnitude more expensive than a local access. Furthermore, you can work on spatial locality, temporal locality, thread locality as much as you want. Remote access continues to be expensive. And it continues to be expensive basically because we don't have caches, and compilers don't know how to compile code that would cache. We don't have ways of taking advantage of spatial locality, basically of aggregation, of bringing variables not one by one, but bringing them in big chunks. It turns out that compilers are not very good in aggregating multiple loads or multiple stores. So remote accesses continue to be done word by word and be very expensive, even if our code has wonderful temporal locality, spatial locality, thread locality, because it's still bringing a word remotely. There is no caching and no cache lines. The performance model is the same as a distributed memory performance model, Local access is very fast, remote access is very slow, which means that you have to write your algorithms the same way you write them in distributed memory. In particular, you cannot do load and store to remote location if you want performance. You are going to bring data in big chunks and copy them to your local memory in order to achieve the right performance. So you get some syntactic sugar that looks like shared memory, but you get a performance model that's distributed memory. And that's why thinking about the performance model is very useful. It's not what is the semantics, but what is the associated performance that really determines your coding style when you want to get really good performance. Can we do a shared memory-like programming model for distributed memory? It provides a shared memory performance model. Some may think it's totally infeasible. It's still, in my mind, a research question. Of course, the question will be, you can do it if you restrict your program suitably. You can do it trivially if you never go and access remote data. But that's clearly too strong of restrictions. Other restrictions, they still allow you to write the codes you are interested to write and allow this model to work. I didn't speak about vector units. I think I'm running short of time. Let me point out just that it's the same game as anything else. You can do it very explicitly. You can totally ignore them. Compiler is supposed to handle them. It works provided that you have a programming style that makes vectorization possible. So it's the same thing like for shared memory and locality. You have to write code to obey certain stylistic rules to make sure that the loops vectorize. And there are, 50 years of experience on how you do that. So people know, people have forgotten, people in the Cree area certainly knew how to write loops that would be vectorizable. So again, an example, the performance model is, you don't need to know that there are vectors, you just need to know that floating point rate is much higher. The reality is that you have to obey some constraints in the way you write to code in order for that virtualization of the vector units to work. Distributed memory programming. What's the main difference between shared memory programming and distributed memory programming? Shared memory programming, you really focus on where you compute, and data is going to follow, especially if you have caches. Distributed memory, you really focus on where data is going to be and try to make sure that compute is happening in the right place with respect to your data. In any case, you have to make sure that computation occurs where the operands that you need to compute are, so there is no difference. The question is, in my mind, where do you start? Do you start by deciding where you compute and then make sure the data is there? Or do you decide where is the data and then make sure the computation is there? In shared memory, communication is reasonably fast, so it's easier to focus on where computation is going to be. In distributed memory, communication is expensive, so it's easier to focus on where you put the data and then make sure that you always execute computation in the place that is most efficient for that, given the data distribution. Distributed memory algorithm or distributed memory focuses very much on how to partition data. Typical assumption for all the languages designed for distributed memory, PGAS languages or MPI or anything like that, is that you have a set of locales. Typically, a locale is a node, but it could be a higher level abstraction. So as I said, a global address is a local ID and local address within the locale. And now we have to split our big arrays that we are using when we do whatever Krylor preconditioner or other things. We need to split them across the locales. So we have a distribution, and typically these partitions are fairly static or slow changing because it's expensive to move data. We partition our arrays. If we write in MPI, we have to do it very explicitly. So in MPI, we have a local view of data. Basically, we have to very explicitly say which part of our big array is on the local node, and we access it with a local address. In PGAS languages, we can also support a global view of data where we think of the data as a big array, not as a chunk of small local arrays. And we can actually access the data using an index, and the runtime and the compiler translate from the global index into the array into a local address. If we have this example, that's a UPC example, if we have an array which is partitioned into chunks, given an index into the array, if I know what's the size of the array, I know what is the size of each of these blocks. So I can compute what will be, on which node element I will be found by dividing I by the block size. And I can know what is the displacement of this element I into the local block by taking the remainder from the division. This is convenient at some level because I don't need to think about how the data is distributed. I can use my global indices. And if I change the distribution, I don't need to change all the computation of my indices. It's inconvenient at another level because these expressions can be quite complex and expensive, and the compiler doesn't do always a good job in optimizing them away. So that's data distribution. The same thing is true about distribution of control. If you write MPI, then you write a local code. You write what code is going to be executed on the locale. You have very explicitly partition control, and you write a local program that uses local addresses. The other possibility, which is pursued in languages like Chapel, is that you really write one program, one global control expression that says what happens on all the nodes, on all the locales. So you may write a parallel loop, and you don't say on which node each iteration of the parallel loop is going to execute. How is that going to be determined? Perhaps by a wonderful compiler that figure out what is the best place of executing each iteration according to where the data is distributed. It finds the location which will require the least possible communication. Or you can actually have a user control of it using a form of an on statement where you say I want this iteration to be executed on a locale that contains AI, for example. So you control, but you don't control explicitly on which locale. You control how your parallel iterations are going to be aligned with respect to an array distribution. Again, very convenient. The distribution changes, the number of nodes changes. You don't have to repartition to change your control structures. So nice performance, less nice, because it's very easy to write lousy codes when you write in this global model. You don't immediately see what accesses are local, what accesses are global, so it's very easy to write low-performing code. But that's a debate that goes on in the community of people working on parallel programming languages. Should we provide a global model of control and of data, global view of data and control? Or should we prefer a local view, or should we think of programming models that support both of them? And I don't know what will be the end point. Well, we saw that using a shared memory programming model on top of distributed memory is hard. Can we do the reverse? Well, the reverse actually is quite easy. You just think of your local memory as a bunch of partitions. You are going to have each core work against one partition of the local memory. If these cores want to communicate, they are going to do put gets or send receives or what have you. Works like wonder. Typically, your shared memory is very good at moving messages. So it's goodness. You can do distributed memory in shared memory. The problem is, of course, you lose some of the flexibility because threads now cannot migrate as much as they could before. Using shared memory just as a medium for copying data is not very efficient. It's much more efficient to access directly the remote data. This programming style is actually used quite frequently, and quite frequently actually it gives you good performance because it forces you to think of locality and you achieve good locality, but it's not ideal. And a lot of work is going on trying to understand whether you could have one model that's implementable efficiently both on shared memory and on distributed memory. If we don't have such a model, then we have to use hybrid programming, where we use one programming model across distributed memory, like MPI or a PGAS language, and another programming model in shared memory, like OpenMP or pthreads, which is by itself a hassle. But it's not clear that you can have one programming model that can run well on both. It may be that we shall get there just because shared memory looks less and less like shared memory, as we heard from Peter Krogi. So we already know that reducing communication is essential for performance within shared memory as well as across distributed memory. We heard that we may not have coherence. So in any case, shared memory of the future may not be what shared memory of the past has been. So we may need anyhow, even on shared memory, some programming model that allow us to control communication in a more direct manner. And actually, I think it's feasible. When you think of a cache, cache is four things. It's a local memory that's close to the physical thread. It gives you the address translation. When data moves to the cache, you continue to address it with the same address. Doesn't change name. So that's the virtualization of memory. Data is transferred implicitly. You do a load, data comes to the cache. You don't have to do an explicit put or an explicit get, and you have coherence. One is clearly essential. No matter what will be the future, we shall have memories which are close to the thread and faster. Two, address translation. It's expensive. Content addressable memory is much more expensive than a regular memory. But I'm not sure that the right mix of hardware and software could not preserve the fact that you think of a cache as a content addressable memory. To give a simple example, if you are accessing data via a pointer, you could think that the runtime and compiler make sure that you swizzle the pointer and have it now point to your local scratch pad rather than to the global memory. So you did the address translation, but you did it statically when you brought the word into the cache rather than dynamically whenever you access it in the cache. Or once when you moved it rather than each time you access it in the cache. Transfer is implicit. We certainly do that even in distributed memory. It means that when you do a get or when you do a load and you know the load is going to be more expensive, then you immediately context switch. People working on shared memory have used simultaneous multi-threading or concurrent multi-threading to do that for a long time. We start doing that increasingly in distributed memory to hide the latency of gets. You need to be able to support many contexts and to be able to context switch fast across those. That's not too onerous. For coherence, as we heard, is too expensive. Furthermore, I would argue that for most scientific codes, it's really not needed because the access pattern to shared data is very regular. You know, at one point in time, these particular variables are updated, and they're updated by the owner. At another point in time, they're read, and they're read by some bunch of users. So you don't have to deal with coherence at the granularity of caches or small objects because the code is very regular, and you go through phases where variables are read or exclusively written, and you can do the coherence at a much cheaper way in a global sense. Let me get to the question you were asking, breaking abstractions. If you think of HPC evolution, in a sense, the question was not that important because what we had is long periods where all HPC machines were looking more or less the same. So we had a long period where we had vector machines and a long period where we had single core clusters, then a long period where we had multi-core clusters. And now we start having accelerators. I call that punctuated equilibrium. You know, long period of stability, period of fast change, long period of stability. Those that are familiar with modern evolution would recognize where it comes from. If we are in a stable period, the question is somewhat less relevant because all the machines are more or less the same, so you don't have to hide them, to hide the vector or hide the multicore and so on. All machines are the same, so your code is portable anyhow. If you are in a period of fast evolution, then you have a problem, And you want this mythical portable algorithm that hide all the details of the machine but run fast on all the machines. So we are in a period of instability. First of all, I'm afraid that we shall continue to be in a period of instability for a long time. And there are various arguments that one can make that the convergence that we saw in the past will not happen now. One reason, for example, is that Moore's law starts to slow down, so you need more invention at the architecture level to keep performance going up. Another reason is this 11 dimensions of Peter. You have more dimension, you have more local maxima that different vendors may pursue. It's not clear that there is one right solution. And we can argue, but I think we may be in a period of continuous instability. And then we need this encapsulation. The ideal thing that Pete will tell you to do, you have a high-level code, you have a wonderful magic compiler that hides the fact that you have vector units or GPUs and so on, and gets you to your different platforms. The reality of how codes are written is that you write a code for one platform, then you add some if-defs and do the modes for the other platform, then add more if-defs and do the modes for the third platform. And codes are not encapsulating unless you consider an if-def to be an encapsulating construct. So we have a problem, and there is a fundamental issue here. Now, can we achieve this ideal that Pete spoke about while we target architectures that are going to be very different and while we care a lot about performance? The issue about programming model is less in my mind what is the ideal programming model that everybody going to use, but what is the programming model stack that we are going to use. And probably we shall have one or more higher level programming models which are closer to the application. One extreme is the notion of domain-specific language, and one or more programming models which are closer to the architecture and maybe different ways of going from one to another. And yes, we would want the translation to be as automated as possible so that you write at the high level and don't worry about the low level. But no, probably you will need people that also program at the low level in order to get the right performance. Now, the interesting question, can you have, and that's essentially what we do, some of the low level is done by libraries or various form of using generic programming and allowing code to be mapped. But the interesting question, can you have a user mock around with code here and still be sure that you translated the top level code correctly in terms of semantics and preserve the performance model? And that's where very interesting research, I think, has to happen, not directly related to high-performance computing, but extremely important to high-performance computing, how you can have these stacks of multiple programming model, have the maximum help you can from compiling, auto-tuning, what have you, to automate the translation, allows the users to tweak the translation, but make sure they don't screw up the semantics.